Hello, hello. Have a seat. Yeah, just before we go to the application session, there was something I realized that I have not told you, and this is probably the good time to tell it. So, if this is your first time to Svalbard, about now, you should start feeling a bit funny in your eyes and in your throat and in your nose. You just feel dry, and that's because you are dry. Your body loses water. Oh, yeah, there we go. So you need to drink like Craig, but water. So no joke, drink a lot of water because the air here is immensely dry, and that dries up your system. And you feel it in your eyes first. There's a water tap outside the lecture theater. It looks like a beer tap, but it actually, yes. So it's water that you get out of there. Use that, drink enough. You will feel much better.
Okay, I'm Kathleen Jones from the Jet Propulsion Laboratory, and I'm one of the leads for the applications topic.
No.
Okay, now.
Yes.
Okay, good. Yes, Kathleen Jones, JPL, and I'm leading this session with Ben Holt, my colleague from JPL, and Michaela Corvino. So let's see. So we have applications is a very broad topic, and we got submissions abstracts for maritime security and marine slicks. But as you all know, applications for SeaSAR are very much broader. So Michaela is going to cover the maritime security topic. I'm going to cover the marine slicks and spills topic, and Ben Holt is going to cover everything else. And I want to say that there are a few topics that I think should make it into the white paper, but that we did not get any submissions for and are going to have to spend a little time on. And one is, in particular, the issues having to do with climate change and the impact to coastal communities. And so tide and wind driven flooding and submergence is going to be an increasingly large issue. It's already a large issue, and it's something that certainly the wind and wave community here could contribute to. And coastal erosion, there was one abstract submitted to the methodologies and techniques session, but that's something that we also should consider. This is something that's going to be cross-disciplinary because coastal erosion really is something that really needs a lot of input from the wave community for improved modeling. So I think that that's something we should also consider in the white paper. So before I start, I want to talk about our breakout meeting organization. The first breakout, which is this afternoon, will start with the presentations on maritime security. That'll be about 1 hour, and then followed by 2 hours of discussion on maritime security, the first hour this afternoon, and finishing up the second in the first breakout on Friday. Following that, the SLIC presentations will be done on Friday morning, and then the SLIC discussion in breakout number 3, and breakout number 4 will be devoted to the other topics. You know, this is a rough outline, but we're trying to make it so that everybody gets to present something for their abstracts, and we isolate the discussions to specific topics. Now I pass it over to Michaela, who's going to take over topic.
Thank you, Kathleen. Good morning, all. I'm Michaela Corvino from the Data Application Division in Esrin, the Enterprise section. So I will give some example of application of SAR, and not only SAR relevant to maritime security. Sorry?
Move it closer.
Is it better now? Okay. Some elements that we are covering within our activities, our research activities, on top of the topics that will be presented also later today with the breakout section. So, as a general introduction, of course, the use of SAR for maritime safety is very well known, is adopted in operational way. So we started, ESA started the GMS service elements that then were made operational, for example, on services like Copernicus Maritime Security. But there are still some activities to be done for a wider and optimized use of Earth observation for maritime security. In particular, there are still several needs, for example, for a more persistent temporal coverage, and so the possibility to access new data, because a maritime community, maritime security community needs always to get several data to cope with, for example, conflict in the acquisition and the request and high number of requests. Then, of course, there are still, even if there are operational service chains, for example, based on traditional methods like CFAR, for the automatic detection of target, and also automated processing chain for the correlation with the IS data, there are still some issues that are relevant to, for example, false alarm detection. And this is really an issue when we work on at operational level, because usually maritime security, the use of Earth observation data, it's always coordinated with patrolling means. So usually Navy, national navies or Coast Guard, they use airpass, they use navies and so on to verify the information that are provided by Earth observation imagery. So in particular, we will discuss about methods to improve target detection, identification and tracking. And then, of course, there is also the issue of the coverage and the near real-time and quasi-real-time service delivery. That is also an important topic for the maritime security community, but this will be not addressed today. So, general information about classical methods, techniques for the moving targets. That is, of course, an important focus for maritime security. So the main techniques are, of course, classical one, traditional one, GMTI and ISAR, InverSAR, spaceborne InverSAR. So the GMTI is used in particular to detect and extract position and velocity on the moving target, and it can exploit, these techniques can exploit both multi-channel SAR, but also single channel SAR. While the InverSAR is used to focus movement targets and also to extract kinematic parameters. In particular, in this case, the target translational motion are compensated usually by using autofocusing techniques, while the target rotational motion are compensated and kinetic parameters can be extracted, for example, through cross-range scaling. So additional details about the ISAR imaging, even if today in the breakout section we will have a dedicated presentation on that. So conversely to SAR, the ISAR approach exploits the target motion and not the radar platform motions to achieve the synthetic aperture needed for the SAR radar imaging. Of course, there is a totally different, there is a perspective change, and in particular, the motion of the target is unknown and must be estimated by from the radar itself. So in both cases, the across-range imaging is resolved by the relative radar target motion, and it's characterized by the composition of two main elements, the linear relative translation between the sensor and the target, and the rotation motion. So the typical SAR defocusing effects. So for moving targets, the application of focusing produces some defocusing effects that have an impact and degrade the range and azimuth resolution, and also produce azimuthal displacement. In particular, we have that the range velocity components is responsible for the shift of the target imaging along the azimuth direction, but also for the smearing along the range. And the range acceleration and the azimuth velocity produce the smearing and the focusing along the azimuth direction, and also signal noise to ratio losses. So the ISAR refocusing process, it's needed to remove, it's applied to remove smearing effects, but also to estimate motion parameters. So an outline of the ISAR processing. So the composition of the radar platform and the target movements is modeled as superimposition of the relative translation motion between the radar platform and the target, and the 3D rotation between the radar platform and the considered target along 3 directions. In order to retrieve motion parameters and also to correct the defocusing target, usually ISAR processing maximizes the image contracts by 2 ways. The first is the compensation with respect to the translation motion and the stabilization on a fulcrum point using usually autofocusing techniques and PGA. And then there is the compensation with respect to rotation, in particular using applying cross-range scaling with the subaperture and again PGA. So some example of results from one activity that has recently ended. On top left, you can see an example of the processing chain. On the left side, there are some examples, the area of interest and the outcome of the processing chain. So we can say that the refocusing is strongly dependent, of course, on the vessel motion, but a contrast improvement is generally achieved. And of course, IS data are usually used for the validation of this of the processing chain. So the inverse allows to enhance the image contracts, to remove or mitigate the effect of the target defocusing due to its motion, but also to retrieve information on parameters. In particular, the parameters of interest can be, for example, the target size and orientation, but also dynamical parameters such as the type of motion, which can be estimated and could give additional information on the activity, on the specificity of the target of interest. And so we are working to better to increase, combine the hybrid SAR and ISAR processing chain, and additional improvements, for example, could address, in particular for a specific case of maritime surveyors, where we have complex rotational movers, maneuvers of vessels, which can determine, in particular, changes in the imaging planes, and in this case, they will require more complex cross-range scaling algorithms. But additional developments, we could look into the exploitation of multiple frames, for example, using applying subaperture techniques, showing the same targets on different image projection plane. We will see later some example on video SAR, but also by considering, for example, different configuration modes, for example, bistatic or multistatic SAR, and eventually also multiple parametric channel. So now, looking at the spaceborne and other kind of products. So the spaceborne, the so-called video SAR. So microsatellite now, the platform are more agile and have mechanical pointing capabilities that allows to enable very long dwell, steering spotlight modes. And so the SAR video are generated by focusing adjacent portion of the synthetic aperture. So every focused sub-aperture corresponds to one frame of the SAR video. And this kind of product could be of interest because, of course, can provide additional information of moving targets. And in any case, it's an additional data set. And as I said at the beginning, usually the maritime community needs to have additional coverage. So Image information algorithms using usually the state-of-the-art is based on subaperture extended chirp scaling processes, which demonstrated also enhancement compared to BP algorithms, back projection algorithms. Also here, we are about to start some activities because, of course, moving target recognition is an important application. It's an important application for maritime security. So videos are moving target detection methods could be further analyzed and also tested over real data set for monitoring of slow speed monitoring moving targets on the ground. And one example is, for example, the one presented before by ISAI. Of course, optimization is needed also to get real-time focusing of moving targets, and we are also evaluating additional applications which are not relevant to maritime security. Now another topic, also here, this is still an exploratory activities. We are also considering, we do not have this example is from literature because so far we are about to start new activities on this topic next month. So the mechanical vibration or rotation of target or structure of targets, for example, the engine or the rotating antenna, may induce frequency modulation on the returned radar signal, which generates bands about the target Doppler frequency, and this effect is called the microdoppler. So the signature, the modeling, and the extraction of information from this can determine some properties of the target that could be of interest, of course, to better characterize the target. So, as said before, the use of microdoppler signature for target classification, identification, and classification is an emerging technique. There are several issues. It's a complex technique. In particular, of course, the impact of different states on marine targets micromotion extraction, and this is the reason why those techniques needs to be tested over a real use case scenario. But also we have that the spatial resolution and the signal to clutter ratio issues for the extraction of signatures for small targets in particular. Then there is another point that the vibration is linked to time-dependent aspects, and for this reason, the ideal condition for the validation is to have acquisition for the ground truth measurement simultaneously with the SAR imagery application. And in general, it's the validation is quite challenging and it's needed the strict coordination with the measurement campaign are critical. So we are planning to further develop activities for the modeling of microdoppler effect and for the extraction. And we have noted also, not only also for target identification, for better target identification, but we notice also an interest from the ISAR community to analyze the compensation of the micromotion in order to improve the focusing ISAR imaging. Then another topic that is, of course, very relevant to the maritime security. We know that SAR imagery alone are not enough, so it's needed to complement there with information from other sensor and system, and we try to use all of them because the full understanding of the maritime picture, of course, requires to have a knowledge of the vessels for both the static and dynamic characteristics. So, of course, the static one are the sites, the type, but also information that can be provided by IS, for example, the flag, the age, the ownership, the port of destination, and so on. And also dynamic, which could be, for example, the speed and heading. So also we have to consider that the capability to detect and track vessel of interest is totally different, for example, when we look at coastal zone. For example, when we have usually a coastal radar which are owned by member state, or in open sea, which where we have, for example, wide coverage of satellite IS, but also air and sea assets. So, of course, we try to exploit all of this information, so not only SAR, but of course also optical and also IR when available, but also it's important, for example, to have correlation to analyze, also to integrate risk register vessels within the overall picture, in particular when we have to analyze activity, anomalous behavior and activities for a specific target of interest. So, of course, this is an example from our one of our project. This is a Cosmos Skymed acquisition, and we have that here. The same target is seen by there is a vessel detection from Cosmos Skymed imagery, but the same image is the same target is seen also through the IS data and through satellite radio frequency. So some information on this. So of course we have the use of IS data is operational. We can derive very important information about to identify the vessels and also to track the vessels, information to generate tracks, but also anomaly detection, risk assessment, and also the analysis of pattern of life. But of course, as we know, IS was meant as an anti-collision collision system, and so it has also a lot of issues, because IS can be spoofed, can be switched off, can be manipulated, and so on. So it's not really alone, it cannot be considered a reliable source of information. Now we can rely also on this new source of information, which is the maritime radio frequency detection. So thanks to opportunities that are offered by commercial operators, but not only, also there are also dual system. In particular, one of the company who is providing the first one, I think, is OK 36 from UK, which now is subject to the ITAR, the International Traffic in Arms Regulation. So it's not so easy to get, no more easy to get information for civilian application, and they work in particular with emission in VHF and L-bands. We are already working with a French company that is Unseen Lab. They are doing acquisition in S and X band. And we are also starting with the one company from Luxembourg, which is called Cleospace, and they acquired in UHF. But there is also a Norwegian company, Norsat, which provides IS and navigation radar detectors. Also here, there are some improvements that are needed. First of all, the good news is the increased availability of radio frequency dataset, because now we can count on more and more satellite. And this allows us, of course, to have a better correlation with the vessel VDS from Earth observation, because, of course, we had at the beginning, due to the limited availability of radio frequency-based satellite and also detection, the time gap between the acquisition from satellite and radio frequency detection was very high, so it was not possible to have a reliable correlation. And what we have to do was to correlate the radio frequency derived information, which are, for example, the position, but also the frequency pulse and other information about the emitter sources, with IS and then with the Earth observation. But now, of course, with the increased availability, we can also develop further the automatic correlation with the EO dataset. Of course, with the increasing availability of this kind of data, which are heterogeneous, there could be direct impact on the data fusion complexity. And so this will require relevant computational resources, and we need to understand how this can be compatible with the near real-time application that is usually a requirement from, not always, but very often from the maritime security community. Another point, of course, is the improvement of the route prediction and reconstruction. More than 3 hours, background and foreground, as it is now. which can be done for matching specific use cases, for example, to enable tipping and queuing acquisition. And we are working in particular on that. One possible approach is to exploit deep learning, for example, supervised learning framework for trajectory prediction based on generative models to be trained with a large amount of historical data that are available now, but also to take into consideration additional information, for example, the seasonality of data and also information on the type of the vessels. Or we can still use statistical techniques based on bias and inference and taking into consideration vessel motion models and also suitable maritime traffic models. So there are still advancements that can be done, in particular for DIS long track reconstruction, and to have a reliable correlation with the Earth observation data, and also to enhance, of course, the prediction precision. I think that, of course, the topic of deep learning, it's very important also for the target identification. And that now is also, we are activity in which we demonstrated that also very good result can be provided compared to classical techniques, like, for example, CIFAR. Of course, there are still limiting factors, for example, in case of small target detection, but we are seeing very good results, for example, close to coastal area. So, but the deep learning topic will be addressed today. For the wake detection and for the automatic target detection. And so this is the list of topics that have been submitted. Again, we will have the InverSAR. And so those are the main topics that will be addressed today in the breakout section. So thank you. And now I leave the floor to Kathleen. Thank you.
Do you want to take a few questions?
I don't know, do we have questions? Ma non si usa.
Any questions?
Okay. Thank you, Kathleen.
Thank you. Okay, I'm going to talk about SLICs. For applications, we're looking at marine oil slicks and spills, identification and characterization, false positive discrimination, and shipwreck location from surface slicks. In terms of submitted abstracts, we had 2 submitted abstracts on deep learning methods applied to slick detection. And we had 1 abstract on identification of sunken vessel location from the slicks on the surface, seasonal slicks on the surface, and then 2 submissions on use experiments for characterizing better classification of mineral oil slicks with SAR. So in terms of I thought I would start by talking about the state of the field and looking at what's really happened in the last 10 to 15 years. And really the big precipitating event, of course, was the Deepwater Horizon oil spill in the Gulf of Mexico in 2010. It provided an unbelievable data set for studying slicks. And several of the things that came out of that and have continued being used is the use of low noise airborne SARs for studying slicks. You have UAV SAR, the instrument that Ben and I have been working with, FSAR and SETI. But what the data from these instruments has shown is that SAR is really not limited to slick detection. I mean, that was thought for a long time. But characterization is also possible. And by characterization, I mean identifying thickness, for example, of the slick. Also, these instruments have shown that it's possible to do this, to see these signatures in any of the bands that we have for commercial SARs right now, X, C, S, and L band, if you have a sufficiently low instrument noise floor. And then also a real quantitative evaluation of the impact of instrument noise on the observations by taking these low noise observations and then synthetically adding noise to them and evaluating what happens to the signals that you get. The second thing that has happened is that quad pole data has become available from some of these relatively low noise instruments, either this airborne SARs or RadarSat-2 has a relatively low noise floor quad pole mode. And that allowed systematic studies of the capability of different polarizations, of different frequencies, and of different parameters that can be derived from the radar cross sections themselves for quantifying the oil properties in terms of thickness or emulsification, where emulsification is quantified by the oil to water ratio. The third thing harks back to what we heard earlier, the use of SAR by operational agencies and services, and that really has been made available by the free and open data from Sentinel-1. And secondly, really importantly, is that there's low latency on that data stream. Then additionally, because more instruments are in space doing these observations, you get improved spatial coverage and repeat intervals from this combination of satellite, optical, and SAR instruments. And that's really enabled a lot of better monitoring services, enabled monitoring services at all. And then lastly, the increased computational capability in terms of improved modeling of transport and scattering models for scattering from oil on water. Machine learning methods are just, despite the huge number of publications that are out there on looking at oil spills with machine learning methods, I believe that they're really in the early stages, because the real use of machine learning is going to be doing this full isolation of slicks from all of the different lookalikes. And then big data sets from Sentinel-1 for these studies have allowed, something that's more than just a one-off with these machine learning methods. So to go through what has happened, slick characterization potential from XC and L band. During the Deepwater Horizon, of course, there was a huge spill in the Gulf of Mexico. We flew UAV-SAR, which is an L-band instrument, and published this data showing that if you look at the cross sections for both looking at a strip of oil versus strips of oil versus water, clean water, then you can see a very large difference between the cross sections, and you can see variations in the cross section that correspond, not shown here, but they correspond to features that were seen in photographs that were acquired simultaneously. And then we inverted that and made an estimate of the oil to water volumetric fraction from the L-band SAR based upon that data that we acquired. And we're able to put a limit of between 65 and 85% oil in the emulsions on the surface. So that was really important work showing not only that you could do this, but you could do this with L-band SAR. the second thing I want to show is talk about is the impact of instrument noise on the SLIC normalized radar cross-section and the derived parameters from it. Prior to the availability of data from these airborne instruments, studies reported, volume and random scattering from oil slicks. But after we got data from these very low noise instruments, those instruments just showed the surface scattering dominated. And so those studies were not substantiated by the low noise instruments. So a study was done starting from UAV SAR data and adding noise to it and seeing what many of these parameters that previously had been reported as being sensitive to oil properties, what would happen to the measured values if you added noise. And what's plotted here is the signal to noise ratio on the x-axis versus the parameter value on the y-axis for oil and for clean sea with different values of oil. Noise added to the UAV SAR data, which is a solid line, and then all of the measurements from all of the instruments, regardless of band, and showing that as you got closer and closer to the noise floor, these measurements followed, contamination. So you have to take a new look at what parameters were best for studying oil slicks based upon what's known now about the impact of noise on the measurements. So we're not saying that those instruments are not good for detection of slicks, but they're not necessarily going to be very good. In fact, they're not very good for characterization of the slick properties, because what you're measuring, what you're getting is contaminated by noise, which means that, what you derive from that parameter is going to have something to do with the instrument and not something to do with the surface. So after that, there was studies done with some of these airborne instruments and with RadarSat-2 looking at the sensitivity of these polarization and dependent and polarimetric parameters to oil slick properties. And I just list here some of the early work that was done with by the Tromsø group with satellite SARs, and then work that was done later with some of the airborne SARs. And I just want to show this, what's shown on, so of course you your head is not as fat as other people's, apparently. Okay, so you can look at the histogram of the normalized radar cross-section values for different polarizations, transmit and receive polarizations, and you can compare it to the histogram of values for clean water, and you can set different thresholds for defining something as being a slick versus defining something as being clean. And if you, depending upon where you set that threshold, you'll have some probability of true detection versus some probability of false alarm. And if you look at the different parameters options, then just a low noise instrument, really the best ones are going to be HH, VV, and HV cross sections, the polarization difference, and a few like the first eigenvalue from a polarimetric decomposition. But when you add noise to that, that's shown over there on the right, then you discover that many of those parameters very quickly devolve into having very high probability of a false alarm. And so whenever you look at all of this taken together, then the best parameter for studying oil slicks characterization is just the VV channel. It has the most sensitivity to the oil characterization. HV is also good, but of course the HV channel is subject to noise. And then entropy, which was often used, is even more sensitive to noise. So this is a great finding because if you want to study slicks, then you don't need a copole, both channels of copole channels. You can just have a single polarization instrument, VV instrument, for doing response, for example. Then another thing that's happened is improvement in these oil transport and weathering models. And I show here results from Johannes Rohrs on looking at the effect of vertical mixing on the horizontal drift of oil spills. What that study did was they calibrated their model against UAV SAR data that was acquired in repeat observations over a 13-hour period with something like 30 minutes to an hour between observations. So you can look at, we put 4 spills out on the surface. We had a plant oil simulant, and then we had 80% oil emulsion, 60% oil, and 40%. So different oil compositions, and looked at how those evolved on the surface. The surface slick evolved over time, and then they were able to calibrate their model based upon that data set. And then using that model, they determined that, really, in order to understand the horizontal spreading of oil on the ocean surface, you really have to have an accurate description of the vertical mixing and the oil weathering so that you can evaluate how the transport occurs both on the surface, where wind has a big impact, and on the fraction of oil that's below the surface, where you don't have that impact. And so if just as a demonstration here, I show the simulations for 3 types of oil. The top is heavy bunker oil, the medium density oil in the middle, and light oil on the bottom. And on the left-hand side is shown the surface slick after 10 days after release, summed over many different simulations. And on the right is shown the submerged fraction of the oil at the end of that time period. So the heavy bunker oil, the heavy oil, is not mixed down so much into the vertical column. And so you see a slick that has been moved further in the wind and wave direction. Medium oil is also not mixed down as much as the light oil, which is on the bottom. And so there's a little light oil left submerged, but medium oil left submerged, but light oil, you still have a big reservoir submerged after 10 days. And that submerged volume is basically a reservoir for resurfacing slicks that can then persist for longer in the environment and move in different directions also. So it's very interesting results. And I think this model, of course, is open sourced and available. And then the other big deal is machine learning and big data sets. And there are 2 abstracts that were submitted. Both of these will be presented in the breakout session, but I just want to show some of the results from David Blondeau-Tissier's study. So what he did was he looked at Sentinel-1 SAR images and used deep learning and looked at data that was acquired in the Great Barrier Reef off of Australia. This results have been published, and there's a data set that goes with this project, and that also is available. And you can see in the box the area that is covered from the data set. So I don't know a lot about machine learning, but what they did was they trained it on about 5,000 images, and they were able to determine, isolate slicks from other features, other radar dark features. And on the bottom is shown little thumbnails of the different features. And if it's a check, it means that it was identified as a slick by this algorithm. And if it was an X, then it was identified as not having a slick in it. And for example, the algorithm was able to identify this slick on the bottom right, and but was not able to identify another slick that was much smaller and disconnected. That was up on the that's up there, 16-kilometer long slick. So there is a lot of potential for clearly a lot of potential for this kind of method, given the number of radar dark features that are in this image. Gaps and future development. I think that one of the big gaps that we will address in the future is this differentiation between mineral oil releases versus lookalikes. And I think that machine learning methods are going to be key to that, and that big data sets for making available these data sets for training and testing is going to be really important. Another thing is characterization of the mineral oil properties by thickness or oil to water ratio or type. And for that, we really need more field experiments for algorithm development and validation. And I think this should be done in combination with both optical sensors and also with multiple SeaSAR sensors, so that we can look at multiple frequencies. We can do a comparison between satellites and airborne lower noise instruments. Modeling, of course, transport models are really important. Wave breaking and wave entrainment of the oil, the mechanisms for moving the oil into the vertical column, that needs to be studied in the future. Also, a different type of model, which would be looking at modeling the normalized rate cross-section versus slick properties to determine, how well can slicks really be characterized by backscatter alone? If not, then can a combination of frequencies help you with that? What exactly can we learn about the characteristics of the slick based upon SeaSAR? And then lastly, I want to point out the idea that we have to prepare for spills of new fuel types. Some of these biogenic fuels, not mineral oil fuels. And we really should consider how we're going to detect those, how they're going to evolve in the ocean environment, and how they're going to manifest in SeaSAR imagery. So going back to the second one, characterization of mineral oil properties, I just want to show a few slides from Ben's submission, abstract submission, which is about an experiment that has been done trying to acquire data, verification data, and develop an algorithm for oil spill thickness measurements. So this has been mainly done in Santa Barbara field campaign, where we went out. I should say that this is done in a project that the Frank Minaldo is PI. Ben is also heavily involved. I'm involved on the algorithm side, and Oscar Garcia is involved in doing a lot of the in situ acquisitions. So some samples of taken from the oil surface for thickness, but the main contribution for validation is drone imaging of the slicks in the Santa Barbara area. So the boat goes out, we fly the aircraft, and simultaneously with these acquisitions to provide some information. So the validation data is mainly provided by these drone-based optical surveys. The top shows the optical map, and then there's a classification by thickness based upon that optical map. And then we acquire data with UAV-SAR over the same area, and we've developed a classification algorithm which will also be presented in this in the breakout session, where we try to determine the relative thickness of the oil, and it agrees fairly well with the optical imagery that is acquired. So with that, I think we can take a few questions.
Thank you for the presentation. Just one question. This in situ data will be available openly, or is it a UAV-SAR acquisition that you did? Or?
Yeah, the UAV-SAR data is all open.
Yes, I know, but the in situ?
Yeah, this in situ data is not yet open, but I think one of the outcomes from this should be that we try to open that. It really depends upon, you know, the NOAA, this project was PI'd by NOAA and their agreement with Oscar Garcia from Water Mapping, because that's a private company.
Okay, and the acquisition were full polarimetric at LNC?
Yes.
Okay.
No, it was a full polarimetric at L.
At L, not at C.
Yeah, no.
Okay. Okay, thank you.
Yeah, two questions. One very short one. You have mentioned several times big data, and I wonder what this big data set is for you. Can you please define the big data? What, in your context, what you meant? And the second question regarding the future needs and future gaps, testing sites for the new fuels, are they already predefined where we can apply for, or yeah, how does it coordinate it? Yeah.
So since I work with airborne data, big data is pretty much anything from Sentinel. Certainly not from our data sets. And then no, there's very little that's been done with the new fuels. I think it's something we think about in the future. I just wanted to throw it out there.
In your understanding, what is big, what you mentioned? Because there are several communities with different technologies. I'm just not sure.
Yeah, I don't really classify it by volume as much as by diversity of the slicks. You're not, turn it on.
Yeah, no. In the past, I did put some efforts in understanding the term big data, actually. And it's a buzzword, and it has, the meaning is not clearly defined, but I think what we are doing here with SAR, even when we have petabytes of data, is not considered as big data. Okay. So big data is more than just a data set which is big. So just to wrap up, there are other aspects of volume. You said diversity, for example, it's a very important part, but the velocity of data processing, the data veracities, there are the concept described of 5 V's, which is actually correspond to big data. So big data means also all the infrastructure, the high performance computing clusters and so on involved in processing all this stuff. So all together, the connection of all the different techniques is big data. So I think when we talk about big data here, we mean actually that we have a very large data set. But I think Google or Microsoft might disagree because they are doing the actual big data.
I'll change it to sufficient data, which is equally ambiguous.
Very nice talk. I have a question about if you can expand on maybe the biological slicks or natural slicks versus oil, and what you maybe just more details on how we can
Yeah.
decipher between these two in the SAR imagery, or what kind of other ground truth data do you need? Do you need any of that, or can we get everything from the imagery?
I will leave it. That's the topic of the next presentation. That you do.
I guess. Let's see, this way. This way? This way. No, this way. This way. Where's my mouth? Let's see. Say the question again for my little brain, my old brain.
I'm just curious of how you're
Oh.
going to decipher between biological slicks and oil slicks, what the methodology would be to do that.
Well, one thing is location. Another thing is persistence, I think, and repeatability. But Werner kindly included me in a paper that Kathleen mentioned about separating oil, looking at slicks, basically, both mineral oil and biological oil. And it looks like one way to do it is with copolarizations, basically. So if you had, a quad pole system, you could probably actually separate it clearly within your channels. But there's, there's not that much mineral oil, really, that's on the ocean surface, and they can be seeps. There's hundreds of seeps in the Gulf of Mexico, for example, and that's why we went to Santa Barbara, because it's a persistent seep area, and then the rest of the world has got surfactants on it. So I think there's some timing and location that can be considered, and maybe they don't look alike in a sort of a shape feature. I don't know. It's a hard problem, I think, because you also have to think about low winds. So, okay. So I'm not very pleased with these slides, but I'm tired, and I did them mostly last night. But I think we'll able to grab them in the white paper a little bit more. But my 4 topics, and I'm sure there's many more that could be brought up, and we'd be happy to have that kind of discussion in the breakout session. Oil and ice, iceberg detection, and just some thoughts about all these. And macroalgae, which could be actually more of a science and not necessarily application area, and surfactants, which also could be considered more of a science research problem as well. So this is just based on the U.S. Coast Guard International Ice Patrol. So this is an example. I think icebergs can be well detected with SAR. So their charge, and this, the Ice Patrol goes back to the Titanic. It was started after the Titanic. So their charge is really to monitor icebergs coming down along the Labrador coast from Greenland and seeing what persists, what stays, what moves into the major shipping lanes. And so by the time the icebergs get down there, they're often small, and they haven't completely melted yet. So they have these programs, extensive aerial reconnaissance, these extensive shipping or examination periods with different kinds of satellites and airborne instruments to identify these icebergs and monitor them as they move into the to the shipping lanes to provide warning systems for navigation. So what they really need, the Sentinel acquisitions have been very helpful, along with RadarSat and RCM, I think. But what they really need is finer resolution to worry about these very small icebergs that are hard to see, that a ship could run into, may not have much of a presence on the surface actually either. And so, and they need reduced latency always to put in their models. And it turns out that they take these observations and they run them, ingest them into an ocean circulation model. So they also NOAA related, so to propagate the drift patterns into the shipping lanes. So these are theoretical questions, I think, because I don't think there's been a major oil spill that I've heard about in the Arctic with the reduction of the sea ice cover and the increase in shipping and exploration. So we've been involved with a couple theoretical studies. The first one we did was, what if there was a spill in the marginal ice zone where there was a presence of new and young sea ice, which basically has both the oil and the young ice have low backscatter signatures. So we put together a couple papers where we utilized collections of airborne imagery of sea ice and of the oil slicks, in this case, the Gulf of Mexico, and also satellite data in the second study, and developed a simple model based on the properties of the sea ice and the scattering of the oil, including dielectric of both components, and that in theory, multiple polarizations would be useful for separating these different kinds of conflicting low backscatter signatures, where the oil may be present within the new ice and hard to separate. And of course, the low noise floor is important. There's been a lot of work on looking at oil that's in the ice or has spilled on the ice, on the surface, has moved through the ice, or might be even under the ice. And this, in theory, would be related to platforms, production platforms offshore. So the paper by Wilkinson provides an overview of response options. And then there's been many studies, including in situ work and lab work that involving penetrating radar and SAR and optical sensors to try to figure out how to do this. So if there were a spill, then the ice is going to be moving as well as changing the oil and moving around. And so how do you track this oil and ice situation? So I guess for me, the key issue was that the similarity in the dielectric constant between thicker sea ice and oil, which is sort of like 3 to 5 parts, imaginary real parts. And but it turns out that I think at cold temperatures, oil changes properties sufficiently that that it becomes possible to separate from the ice itself. So this is again, theoretical work and sort of preparation for potential, kind of a real operational problem in this remote part of the world. So SAR detection of macroalgae is another application that's kind of turns out to be pretty interesting. And I remember an early conversation I had with Ramon Husong. he says, Ben, you can use Sentinel-1 data to look at sargassum. There's been some studies, and it turns out the sargassum signatures are actually brighter. They don't show up as slicks, but they show up as brighter than the surrounding ocean. So a study was done that I was invited to participate in with investigators from the University of South Florida who were mostly involved with optical detection of sargassum and macroalgae elsewhere. So they, using Google Earth Engine and a machine learning, I think, technique in Google Earth Engine available, they ran a series of collections over using Sentinel-2 and Sentinel-1 for several years. And for 3 different types of dominant sargassum, or dominant macroalgae. And it shows that actually here's one example which doesn't show up very well, but you can see the bright signatures of the SAR in the lower right panel. And they'd already developed some of these techniques. So the technique to separate the sargassum with Sentinel, the color data was already done, and some preliminary work on the SAR as well. So this is basically a machine learning task to see what was going on and to verify that these SAR signatures were actually what they seemed to be, as brighter. So it does turn out that the signatures, the ulva, the type of macroalgae on the left side, is in all cases when the SAR identified the macroalgae, the signatures are brighter than the surrounding ocean. And I believe, and what we wrote in the paper, was that it's due to in a higher density biomass situation, that there's a lot of the leaves, the components of the macroalgae and the stalks and so on, imagine kelp, for example, are present above the sea surface and creating some sort of additional scattering. Maybe they're actually little radar antennas in a way like frost flowers are in sea ice. So they have an enhanced scattering, which is surprising because you would expect them to be reduced scattering, which they are in other times of the year when there's less density, I think. So the combined sensors actually led to a higher number of total observation and better capacity to monitor the spread and location of macroalgae masses. So the most relevant situation has been this incredible explosion of sargassum that's formed in the central Atlantic and is transported into the Caribbean and the Gulf of Mexico. And this has led to the stuff just is carried onto beaches and affects the tourism, and it creates this big problem with the collection of this massive amount of weeds on the beaches that have to be kind of cleared up because they start smelling, and really unpleasant situation. Nobody really knows why there's been this explosion in the last decade or so, but there may have something to do with humans and related to fertilizer runoff through rivers. So it's may not be just a natural situation, occurrence of increased nutrients, let's say, and the change in the transport of this algae into as it's formed. So this is a MODIS example that was published recently, but the University of South Florida has a monitoring program for this type of macroalgae. Now, biogenic slicks. So I have this biological term, exudates. So this is stuff comes off of marine plant and animal growth cycles, basically. So it's all the little floating parts that help plankton stay near the surface. And as they grow and die, the stuff is released and forms this microlayer. It has, turns out it has pretty much a global distribution. And recent studies have really shown quite a lot that it has an can have an impact on air-sea fluxes, including heating, gas exchange, and so on. And we know particularly in the nearshore coastal regions that they can be formed into these convergence lines, which are basically indicative of near surface circulation. So it acts as a tracer. So how to separate? You know, it looks like you probably really need cold polarization, but I think you also have a timing, persistence, and location capability that you can be utilized. Actually, this was presented in the methods section by a group from France, I think, including Roman, as using the Ralph and Justin's machine learning output from their wavelets, the imagets, and looking at a more depth situation within the Mediterranean. And I think this is ripe for a kind of a situation that ripe for machine learning, because you probably need multiple sensors. You can confirm the biological component with chlorophyll, perhaps, probably, very likely, as Werner showed years ago with a combination study of winds and SAR and chlorophyll. Remember that paper? I do. And has an impact on as a colleague Tim Liu found years ago, that it has an impact. If you have an extensive amount, it can have an impact on the scatterometer retrievals of wind. And so there's been a lot of work on surfactants by many authors. I'm sorry I haven't listed everything or included nice pictures. Well, here's one nice picture coming up, as we've seen. We haven't talked too much about submesoscale slicks and eddies, but this is something from Martin that he gave me yesterday, which I have many examples where the slicks can, basically serve as tracers of the underlying circulation as they form into these narrow bands, which are convergence lines. And then lastly, Martin, this is from Martin Gotti as well, has just started a study that's looking in a lab. Right now it's a lab situation where he's looking at wind flow over near surface wind flow over slicks and non-slicks. I think that's right, Martin? And finding out that that there's more turbulence in the upper ocean when there's no slicks present, and at the top of the waves, basically. And when there are slicks, you have less turbulence and and an increase in the wind stress. Is that right? Something like that? Pardon? Decrease. Yes. Okay. That makes sense. So this seems to be really interesting study that he started. Okay, I think that's, oh, here we go. Surfactants. So that's about all I had. I'm sorry I don't have a great summary, but I think there's lots of applications that using SAR that need to be continued and can use more observations, of course, and more study and actually may have the potentially a regional and global significance to look at a lot of these low backscatter signatures and to be prepared for potential accident in the Arctic with increased activities. Okay, thank you. Questions or comments? All good. What else? What else did I miss? What did I not include? Water quality, coastal processes, stuff like that.
Don't go. So I think we have time for discussion before lunch. So any questions for going back to Michaela's presentation or mine or general questions? Ernie?
Nowadays, a lot of palm oil is transported by oil tankers. And as far as I know, they can clean their tanks after leaving the port. And so that is legal. And there must be a lot of slicks made up of this palm oil. Have you considered it? Is there any publication on this subject? I think there should be records on the transportation of palm oil and where they clean the tankers in the neighborhood of harbors or so.
I'm not aware of something.
Well, you can still pump bilge oil, right? I think you can still pump bilge oil. I could be wrong about that. Outside the limitations, the country limitations. Not aware of any palm oil. One thing, a lot of the Norwegian oil and water exercises have always included plant oil, as you did too in your early studies back in the 80s and 90s. And one interesting thing that we found with this Norwegian campaign we were on, which I'll sort of briefly look at in the breakout, is that we dropped oil. We dumped this known kind of emulsified oil, which during high winds, the oil just basically mixed and disappeared quickly. The plant oil, in this case, which was kind of a plant oil, actually stayed in place. So it actually didn't spread. It maintained its location while the dumped oil, the oil we deployed, was mixed and disappeared. And so one of another modeling study used this and found out that the both types of oil were getting mixed into the upper layer by waves and wind and the Stokes drift and all that stuff. And so, no, is it? Anyway, this is another study. This is not this one. And that the plant oil mixed down and then came back up in the same place where had been on the surface, while the other oil just basically the mineral oil mixed away. It was pretty interesting, and so it has this distinct quality. The drift component is very distinctive, I think, from the mineral oil.
Yeah, I think that there's probably diversity in the plant oils that might make them different, but we did definitely see deeper mixing of the plant oil than the mineral oil, and persistent resurfacing of that slick in the same location.
Here, I'll put Ben on the spot. We have a little NASA feasibility study to use ICEYES, the X-band commercial radar that was talked about this morning, to look at harmful algal blooms in the Laurentian Great Lakes. And we've looked a little bit, well, Ray has to my left here, on looking at C-band. But again, Ben, do you want to speculate on, are they going to be bright or are they going to be dark? You know, you could probably make the argument that and just for maybe some of the folks in the audience, that when we get a large surface scum from the HABs, we actually get a really big near IR return. And as a matter of fact, you can map it in cloud-free areas very easily by nailing that NDVI kind of index on that thing. But then when it gets stirred up with wind mixing, then all of a sudden it at least looks anecdotally like the capillary waves, in this case, the Bragg wave for X-band are dampened. But have you looked at HABs, or has anybody in the audience, and for example, the Baltic, looked at harmful algal blooms, the toxin ones, and observed either the brighter or the darker return?
So
that may be fun
so
in the
I think,
workshop.
am I on the right one? Here. I think I think the macroalgae really occurs, really shows up when it has a high mass, it's concentrated. I mean, that stuff has, that stuff is like kelp. It has a structure to it. It's all, it's thick, kind of this thick, plant material, really. And so I think that's what's causing the bright returns when it gets so massive and shows up on the surface, above the surface, that it has this material, this structure on the surface, really. And I think that's what's scattering. And I wouldn't anticipate an algae bloom to have that kind of composition, so it would be more like a slick, I think, is my guess. And I think that's apparent with some early, some investigations.
So on one of your images, then you indicated that potentially what you saw in the images was connected to human based fertilization and river outflow. But then what you saw is basically nothing of this evident in the coastal areas where the rivers are meeting the ocean, but you see it first way into the ocean. So what's going on between the outlet area, where you would assume that you have max concentration in the fresh water and corresponding whatever material that is dumped with the river? What goes on between that site and where you suddenly start to see evidence of this possible signals that you want to connect with increased fertilization outflow?
Well, my thought actually of I've just looked at papers and studies on this stuff, and obviously this stuff is it forms in the equatorial Pacific, equatorial Atlantic, and then it moves in, along South America, where I suspect that if there were, well, the fertilizers could come from Africa runoff as well. This is what people have speculated on. Nobody really knows why there's been this explosion of the macroalgae, of this kind of algae, actually.
Did you compare with the model? Because we have a lot of work on this in terms of operations in the West, in French West Indies, and there are also some Olshi Sentinel-3 images, which we are using in our drifting model. So, did you have any experience with this? Did you use or did you check any models or Olshi measurement from Sentinel-3?
Related to sargassum growth, or
Yeah.
No, just I've seen it in work is all. Other studies.
We have with Mercator we have a dedicated ocean model, which is providing surface current for our drifting model for the French West Indies, and we are doing some forecasts on sargassum. Yeah, and in the forcing of the drifting model, we are using this Olshi color, ocean color from Sentinel-3, and yeah, so they are very good. So
I think that what I've read is that there's could be changes in the currents and the wind patterns and so on, and somehow concentrating the nutrients or something like that. I mean, there has to be some nutrient involvement, I would think, as well, to cause the increase.
Can I come in here? Because we're looking at sargassum as well in NOC. And the two current theories about the sargassum blooms are linked to changes in circulation, ocean circulation, and particularly the role of waves, Stokes drift in that. Because numerical models that don't include Stokes drift don't tend to predict the trajectories quite so well. And the second theory at the moment is also this increased runoff from Amazon, possibly Africa too, but it tends to be more concentrated on the western side of the basin. So, but yeah, it's an area of great interest, and I think that's another example where bringing a sort of synergetic view, as Johnny would say, to this would be really, really helpful to understand what's going on.
Thank you. Thank you. Thank you. Anything else? Christine.
Well, before we break for lunch, if there's no more questions on this topic, I thought I'd go back to NISAR's observation plan and just talk a little bit about that. So we are going to acquire data over the Gulf of Mexico and the Caribbean Sea on every pass. It's a left-looking instrument, not a right-looking one, so it's not going to be, coincident with Sentinel or anything like that. We are right now trying to expand the coverage on the East Coast of the US, but as Ralph mentioned, that's a trade-off between, they get 35 terabits per day downlink, and you have to trade off with someone else in order to get those bits, so we're working on that. We also have an allocation of a half a terabit per day for urgent response, and so it is possible that limit was set based on a large hurricane in the Gulf of Mexico, the path of that, and 3 days in advance, how you would track it. So there is quite a bit of allocation for urgent response data that could be acquired prior to landfall of and during a tropical storm development into a hurricane, and even if we don't get the data in the Atlantic. So there's, it's certainly not a priority of NISAR to get ocean data, but there are some options for eking it out if you're creative.
So I think one of the things would be nice will be to try to have some acquisitions as a precursor for what we'll get from Roselle over the ocean, and there's some synergies there. And I just wonder, maybe you have a couple of slides you want to put into the next session, which is about future missions, because we didn't get anything from you guys.
Okay,
So
sure.
if there's 4 or 5 slides, and I'll just add them to the compendium here. And what we're going to do is run through various aspects of SAR ocean data
Okay.
for current missions a little bit, and what we've done in the last 20 years, but what we're coming. So it'd be really useful just to put something in.
Yeah, I'll give you the observation plan, for example,
Sure.
that kind of
Okay,
thing.
great. Thanks.
And a follow-up question, what's the open free access policy to NISAR data then?
It's totally open and free. Any data. L-band is, and actually, the agreement with India is predicated on the fact that the S-band data will also be open and free. We are currently negotiating with them to have both data sets hosted at the Alaska Satellite Facility, DAC. Whether that S-band data is posted as fast as the L-band data is questionable, but it will eventually be free and open.
And you did say that it will operate also substantially over the ocean.
Well, I mean, you're going to get the Gulf of Mexico and the Caribbean Sea all the time. I would not say you're going to get the global ocean for sure.
Yeah. But could be, for instance, out of this workshop as a recommendation, have a hint to possible super sites for
Yes.
NISA.
We can definitely take that back. One big issue with adding data over the ocean, or actually over anywhere, is that NASA wants to know there's a user for the data.
Yeah.
So having it specified as a super site would be very valuable. I'll show you the observation plan. For example, if you wanted to add the Mediterranean Sea, that's an area where there's data loss simply because you're turning on and off the radar and you have to form a synthetic aperture. So keeping it on over some area might be a very efficient thing to do, for example.
Just point out that we're monitoring all the sea ice coverage from both poles with NISAR. It's NISAR, Johnny. I want you to correct it to NISAR. My personal grievance is somebody says NISAR. I don't know why that happened, but some people still do it. NISAR. Anyway, we have complete coverage of the sea ice. We have complete coverage of the sea ice region, and also the Indians have their own requirements. And so they will be actually obtaining a fair amount of ocean data, I think with both poles, over surrounding in coastal regions and elsewhere around it. Just to clarify. NISAR.
That's nice said. That's nice said.
Okay.
No, you don't get this one.
Just one question about the data open access. Is it for all level or just specific, like
Yes.
SLCs and everything? Okay.
Yeah, so there's going to be level 0 data will be available. Yes. And then level 1 data and level 2 data, even people want interferograms, that'll also be available. Within
like a couple days.
within 24 to 48 hours for the whole data set. I'm trying to get the level 0 data posted a little faster so that NOAA, for example, could do their own processing and reduce the latency on that. We're also developing open source processing software that supposedly will also process level 0 data, and you could also process in the cloud on that.
You know that, isn't it called ICE?
I recommend that if you want training on like level 0 processing and those things, there's an early adopter program for SeaSAR, and we can, if you join as an early adopter, we're going to try to have training for that kind of thing.
Is it still the plan to try to leave the radar on for a few seconds, either going from ocean to land and land to ocean or ocean to ice and ice off? Because they were talking about that getting routinely 50, 70 kilometers of coastal type backscatter.
Yeah, that I can exactly how much coastal ocean you actually get after processing is not so clear. There will be some, for sure. They want to get all land and some of the coastal ocean. Yes, yes. Oh, and another thing is all of the Pacific islands and islands will be acquired too, and you got some ocean around those.
So we had the same strategy with Sentinel-2, and there was many people were upset that we didn't have a lot of coverage from Sentinel-2 over the ocean. But the strategy was if a pixel lies within 10 kilometers offshore, then we acquire the entire swath, because that's how you have to do it, right? It's a ground segment nightmare to try and extract just the bits that you don't want now. Now, when you do that, even with narrow swath sensors, you have an enormous amount of data. So yes, the open ocean isn't very well covered by Sentinel-2, but the amount of data you get when you look at the coastal zones and all the small islands is vast. So I think there'll be plenty of opportunities. It would be nice just to make sure that we get some deep ocean examples in targeted areas where we know there's stuff going on. So western boundary currents, etc., would be quite useful. And I think that would be very handy to understand what we can expect for Copernicus Roselle. And I think that probably there must be collaborations already going on. I think in the mission advisory group there is some representation maybe from NISAR, but I have to check. If not, there should be.
Yeah, we should come up with specific recommendations that we can then negotiate on. Okay, anything else? Last chance. Okay, bye.